Aloha and welcome to our video on early astronomy. In this video, we'll describe the contributions of the ancient Greeks. We'll also talk about Copernicus, Brahe, Kepler, Galileo, and Newton. Okay, so let's take a quick peek at some of the contributions to astronomy by the ancient Greeks. Now, first on our list, we have Aristotle, and Aristotle is probably one of the greatest thinkers of all times. However, because of this, sometimes his ideas lasted longer than they should have. He believed in perfect spheres. He thought that the sphere was the perfect shape. So therefore, the Earth would have been a perfect sphere, space would have been a perfect sphere, all of the planets would have been a perfect sphere, and they were perfect. There were no imperfections on them. And this idea kind of stuck and was held around until we see about what Galileo started to discover. Now, Aristophanes, we see here, he factored out the size of the Earth, and he factored the size knowing that its shape. So the ancient Greeks had a really good understanding that the Earth was round, and we can see how Aristophanes calculated the Earth's circumference here. And what he did is he measured, by looking at a well, this angle, and he found an angle to be 7 degrees here. And that angle that he found was based on a well from or a post in Alexandria and a well at Sion, and he was able to see the difference in the sun. That gave him his angle there, and then by calculating how far those two cities were, he was able to calculate the Earth's circumference, and he was pretty close. So a really good mathematical way for him to solve this. Aristarchus is credited with proposing a heliocentric model, and that was kind of against the norm. Man has always considered himself to be special, so we would be the center of the universe because we're the most special thing there. But Aristarchus proposed a heliocentric model. And he looked at stars and the idea of parallax, but unfortunately, all he had was the naked eye. He didn't have telescopes, so his observations weren't able to show that this parallax does indeed occur. And then we talk about Ptolemy. And Ptolemy predicted planetary motion, and we'll talk a little bit more about his in the next slides or so. But he was able to come up with a system of predicting these planets, how these planets moved. Now, the ancient Greeks called these planets because they were wanderers in the sky. So you had your stars, which were more stationary, and then you had these other ones that were moving, and those were the planets. We also have to mention Hipparchus. Hipparchus cataloged about 500 stars that he could see with his naked eye, and we still use his star catalog today. So he proposed a whole bunch of other things, probably the greatest of the Greek astronomers, and if you ever have the chance to look into what he's done, that's a really good person to look into. So some terms that you're going to hear a lot as we're talking about astronomy are geocentric and heliocentric. Geocentric, geo would be Earth, so what we're talking there is we're talking that the Earth was the center of the universe. Around the Earth we would have the moon, around that we would have Venus, and then we would have Mercury maybe, and then we'd have the sun, and then we'd have Mars, and so forth, and out here we'd have the stars. But the key thing with geocentric is that the Earth was in the center. Now, in contrast to that, we have a heliocentric idea, and a heliocentric idea puts the sun in the middle of this. So around the sun we would have Mercury, and then Venus, and the Earth, and then Mars, and so on and so forth. So two different models, you'll hear about this a lot in the lessons. We have heliocentric, meaning the sun's in the middle, and then we have geocentric, which puts the Earth in the middle. Now, we discussed Ptolemy a little bit earlier. We said that he worked with planetary motion. So what he was able to do is he was able to predict where we would find these planets. And what he did is he created up these different systems. Now, remember we talked about Aristotle and we talked about perfect circles. So what they believed is that we had the center of our solar system, whether it was the sun or the earth, and then around that in perfect circles is where you would see these planets. Everything was in a perfect circle orbit like so. Now, this worked out well, and you could see how this would work, except we would notice, and if you see here on number 1, right up here, what we're talking about is we're looking at Mars, and we're looking at the background stars. So what we're seeing in this motion is as we're going, we're going to notice that Mars as a planet against the background stars is going to be moving in this direction. Now it gets to a certain point, and we notice that suddenly it's going in the opposite direction, and we call that retrograde motion. So this here is where we call retrograde motion, where it seems to be moving backwards. And it would do that for a certain point, and then it would resume this normal motion again. So in order to work that ways through, Ptolemy came up with the idea of epicycles. So while you might have a perfectly circular orbit, that planet might be on another circle here, and that would be an epicircle. And then this could have another circle here, and then you could have another circle, and you'd have so many of these epicircles until you could explain all of the motions of the planet. So not a perfect system, but it was highly accurate, and that's why it stuck around for so many years. Now, if we jump into the 1500s, we have two astronomers I want to talk about real quickly on this slide. The first one is Nicholas Copernicus. Now, Copernicus was the first of the more modern astronomers. So we gotten out of the ancient Greek, and not a whole lot of astronomy was going on, and the reason for that is the powers that be believed what Aristotle said, so his ideas seemed to be carried on. So everything was a perfect sphere. We had perfectly spherical orbitals. We could use these epicycles of Ptolemy to predict the planets, so we didn't see a lot of new thought. Copernicus went back and he proposed this universe here. And I kind of want to show you that he went back to a heliocentric. So that means he put the sun here in the middle. And around the sun, you can see that he had the Mercury sphere, the Venus sphere, the Earth sphere. And then around Earth, notice he has another sphere, and this is where we found the moon. Then beyond that, we had Mars and Jupiter and then Saturn. And that's as far as we went. Those were the only planets we knew. And then beyond that, we had the stars. So we had this realm of stars that was the farthest out there. So no knowledge of distance. It was just the outermost edge that we could see was this ring of stars. And while Copernicus's idea wasn't exactly new, it made sense. It got away with some of the epicycle ideas, and it allowed it to be a little bit simpler, and scientists agreed with it, but we didn't have the really good evidence of it. And that brings us to another scientist, Tycho Brahe. And what Tycho did is he was kind of a partier. He liked to have a good time, and he had his own observatory. And for about 20 years, he would go out every night and he would record where the stars were. But he was more interested in his social life than actually doing a lot of stuff. So what he did is he would basically surround himself with great scientists. But he did for 20 years went out and he made detailed observations of where the planets were, where the stars were, and things of that nature. So when Tycho died in 1601, his estate was left to one of these scientists that came to stay with him. And this scientist was Kepler. Now, Kepler was a mathematician by trade, but he was fascinated by the stars. And what he did is he looked at Tycho Brahe's work, and having 20 years of data gave him the ability to look and to see what was going on in the universe and in the solar system around us. And he came up with his 3 laws of planetary motion. The first one is the law of ellipses. And this contrasted with what Aristotle said, but rather than these planets traveling in a perfect circle, they were traveling in an ellipse. And that's a slightly difference. Now, the ellipse might not be great and pronounced, but it was an ellipse nonetheless. And once we switched the shape, then all of a sudden we could get rid of epicycles because everything started to seem to make shape or make sense. Now, the second law is what we call the law of equal areas. And what that says is that in a certain amount of time, a planet's going to move in orbit. The area from the orbital radius to the sun, this little triangle that we have here, and I'll color it in red so you can see what we're talking about, this one here is going to have the same area as any other wedge that we would cut out of that ellipse that passes for the same amount of time. So what that detailed is that our planet seems to move a little bit slower when they're out here, and they seem to move a little bit faster here, and it's the area that's the same, it's not the same distance. And then the third law was kind of interesting. His third law here basically gets summed by this one here. And what it says is that the square of the orbital period is directly proportional to the cube of the semi-major axis. And what that allowed us to do is predict how long it would take for a planet to go around the sun if we knew how far away it was, or if we knew how long it took to go around, we could calculate how far it was. So that helped us finalize the distances and the periods for our planets in the solar system. So Kepler did a lot of math. He kind of corrected our ideas of the orbital shape. Instead of it being a circle, we went to an ellipse. And this brings us to Galileo. Now, Galileo was an interesting scientist. He was very firm in his convictions. He stuck with his ideas. He didn't want to change them. He didn't want to bend them to fit into popular culture or to the governing powers that be, but instead he kept true to his beliefs and his ideas. What made his observations unique was he heard of this thing called a telescope, and then he worked on it and made it a little bit better. And he used his telescope to make observations. And the observations he made were kind of like not so profound if we look at what we know now, but at the time they shook the world. One of the first ones that he found is he looked at Jupiter with his telescope, and he noticed that Jupiter had 4 moons, and these are the Galilean moons. And we'll talk about those when we talk about the solar system a little bit later on. But he noticed that here we have another planet that has moons orbiting around them. Now, up until this time, we had a lot of belief that we were a geocentric. Remember, we said that man is the most important thing in the universe, so obviously we have to be in the center. Well, if we have moons orbiting another planet, now suddenly we're not the center of everything. So that kind of really shook a lot of people's idea of man, because now we were saying we weren't the center of the universe. He noticed that the planets were disks and not simply points of light like the stars. He looked at Venus, and he found that Venus had phases like the moon. And the only way to explain this was not that Venus was traveling around us, but it would be traveling around the sun. So now we had conclusive proof that we had a heliocentric universe. The next two also were kind of disturbing, and these went against Aristotle's ideas. Now remember, Aristotle believed in the perfect sphere. So when Galileo turned his telescope to the moon, he found that it was not smooth. You would expect the sphere to be perfectly smooth, but it wasn't. It was impacted with craters. It had scars and things like that on it, so it wasn't a perfect sphere. Now, this contrasted Aristotle's thought, and remember that Aristotle was thought to be the greatest thinker, so his ideas had to be true. Now we were casting doubt into the whole ideas of Aristotle, and that transcended beyond astronomy. And the last were sunspots. And Galileo would look through his telescope at the sun, so not a very good thing, so he probably had pretty poor vision when he got older. But when he noticed that the sun itself wasn't perfect, and this was really shattering. The moon is kind of bad, but now to say the sun, the most perfect thing that we know of, the brightest thing in our sky, wasn't perfect. And that's what Galileo kind of shot out at us, is he showed us it was a heliocentric model, kind of took away the importance of man, and showed that the universe isn't perfect like Aristotle believed it was. So really some profound ideas that changed a lot of human thought came from Galileo. And this brings us to Sir Isaac Newton. Now, Sir Isaac Newton's famous for gravity, and he found out that gravity alone could be what caused the planets to move around the sun. And that was his idea of universal gravitation. And the lessons will explain that a little bit more. He also started playing around a little bit more with telescopes and working with mirrors and things like that. So he had a much better telescope than Galileo did, but still it was not as advanced as the ones that we can get now. Okay, so those are our early astronomers and their ideas that they put forth. As always, good luck on your quiz, and we will see you in the next video. Aloha and welcome to our video on the Earth, Moon, and Sun system. In this video, we will describe the movements of the Earth known as rotation, revolution, and precession. We'll explain how the moon goes through phases, and finally, we'll talk about eclipses. So the first motion we're going to talk about is the rotation of the Earth, and that's the spinning of the Earth on its axis. The problem is how do we measure when we've done one complete spin? And we have two different methods. We have a sidereal method, and then we also have a solar method. And the results of both of these are what we call a day. If we look at the sidereal day first, what we're using are distant stars. So if we go outside in the night sky and we look directly above, we'll see a star there. If we go out the next night, we should see that same star in that same location, and that would be a sidereal day. Now the sidereal day runs about 23 hours and 56 minutes. So you notice there's a 4-minute differential, and that means that our stars are going to rise 4 minutes earlier every night. So that's why they change throughout the years, because it's not exactly a perfect sidereal day is 24 hours. Instead, it's 23 hours and 56 minutes. The other way that we can mark a day is we can use that star that's closest to us, and that would be the sun. And what we do is we look at the sun, and when the sun's noon rays are shining directly above a point, and we would mark a day as being when those sun's rays are directly overhead again in the same point. So it takes 24 hours for a solar day to occur. And that's about what we use. It's not always going to be 24 hours, but our average solar day is 24 hours, and that's the time that we use for a day. So both of them, what we're doing is we're looking at a celestial object. In the solar day, it's the case of the sun. In a sidereal day, we're using a distant star, and we're seeing when the light coming from that object is going to be directly overhead and crossing the median in the sky. Now here we are looking at two different things. We're going to talk about the celestial sphere, and that'll help us with revolution. Revolution is the time it takes the Earth to travel once around the sun. So while it's not pictured here, what we're talking about is if we have our sun here in the middle and we draw our orbit of the Earth, if we start at this point here, how long does it take for us to travel around? And the result of this traveling around the sun, the end result is what we call a year, but also it's what gives us our seasons, and we'll talk about those, and we have talked about those in this class already. Now, this here, the celestial sphere that we're showing you, has a couple of interesting things. We see our Earth is here. Directly off the North Pole, we have our North Celestial Pole. Directly south, we'd have our Celestial South Pole. We have two lines in here that we kind of show. We have the Earth's equator, and that is going to be straight out from the equator. So if we took the line, our imaginary line of the equator, and extended it out into space, that would be our equatorial plane, and that's what we call our celestial equator here. However, the sun, because we're tilted in our orbit and we're going around, we have this other line here called the ecliptic, and the ecliptic is going to be the apparent path of the sun. So in June, we notice that the sun's going to be a little higher in the sky. In December, we notice it's a little bit lower in the sky, and that's because it follows the ecliptic, not the equator. So that's one of the reasons why our days are a little bit longer in the summertime, because we're tilted towards the sun. So it's going to make the sun appear to be higher up in the sky. Now, the last type of motion that we want to talk about is precession, and you can see it labeled right over here for you. And what precession is it's kind of the Earth as it's traveling around the sun and it's rotating, it's kind of wobbling like a top does. And because it has that little bit of wobble, the result is that our tilt isn't always going to be 23.5 degrees. It'll kind of back and forth and wobble a little bit. But the net result of that is our North Star that is current won't always be our North Star. It'll kind of wobble back and forth. Back in the early Middle Ages, it was actually a star in the constellation Draco, but we've gone through our precessional rotation, and that's caused it to be our North Star now. Okay, so let's talk about the movements of the moon. First thing I want you to realize is that the rotational period, the time for it takes to spin on its axis, is equal to the revolution period, which is the period of time it takes to go around the Earth. So the result of that is we always see the same side of the moon. However, during a month, we'll notice that different amounts of the moon are going to be lit up by the sun. And that's because it relates to how the Earth and the moon and the sun are all related in position. If we start with a new moon here, what we notice is we have a dark moon. And what we're seeing is because the rays of the sun are striking the side of the moon that is away from the Earth. So because of that, we don't see the brightly lit moon. What we do see is we see the light reflected off the Earth onto the moon, so we can still see it in the night sky. Now, as we travel around its revolution, we'll come to the first quarter here. And in the first quarter, if you looked at the moon, it's going to look a little something like this. And what that means is you're going to see half of the moon is going to be lit up and half of it's going to be dark. And the reason for that is because we're at a 90-degree angle with the sun. So because of that, the lit part here is going to show us that half of it's going to be lit up and the other half is going to be dark. We travel another week or so and we get to a full moon. And our full moon here will have the entire moon is going to be full. And that's why we call it a full moon. It's full of light reflecting from the sun. And that's because the shiny side, or the side that's lit up, is going to be facing the Earth in its entirety. And if we travel around, we get to the third quarter moon we see over here. Now, there are some other terms that I want you to be familiar with. We have the term here waxing, and waxing is when the moon is getting more and more lit up. What that means is there's more sunshine hitting the moon So the part of the moon that is lit up from the sun is growing. The opposite of that is going to be waning here. We also see these terms gibbous and crescent. Crescent is going to be when less than half of the moon is lit up by the sun, and gibbous is when it's going to be more than half of the moon is going to be lit up by the sun. So this kind of explains why we have the phases. It's a relationship of the location of the Earth and the moon and the sun together, but also some of the terminology you'll see going through there, like a new moon and a waxing moon and first quarter and so on. Okay, and just like the day, how we had two different days that we could measure. Remember, we're measuring based on another object to mark the transition of time. So in a day, we had a sidereal day where we used distant stars, and then we had a solar day where we used the sun, and we run into the same process with a month. If we first look at a sidereal month here, what we're doing is we're measuring with distant stars. So on day 1 of the month, we'll notice that the Earth is here, the moon is here, and we line those up, we can go out to some distant star. 27 and a third days later, we'll have the Earth and the moon and the star lined up again. So that would be a sidereal month. However, we tend to go more with this synodic month here. And the synodic month is going to line up the Earth and the moon and the sun. So you'll see that all three are lined up here. And then 29 and a half days later, we have that same alignment where we will have the Earth and the moon and the sun all lined up. And that's a little closer to our traditional accepted 30-day month on a calendar. So we can see how it's going to be a little different every year, and every month we're going to have a little variation. But what we're talking about is we're measuring it based on what? So if we measure it based on the sun, we have a synodic month of 29 and a half days. If we measure it based on a distant star, the sidereal month is going to be 27 and a third days long. All right, so let's talk a little bit about eclipses. A solar eclipse is when the moon is going to travel in between the Earth and the sun. And what it's going to do is the moon's going to block out that sun. Because the sun's so far away, we can block out the light that reaches the Earth that way. And we're going to end up with a couple different things here. We'll have the umbra, which is the darkest part of the shadow, and we can see it right here. And that's going to leave a line on the Earth of transition, of when it's moving, and that's going to be our path of our total solar eclipse. So during a total solar eclipse, that's what you would see here. You would see a little bit of light coming around, peeking around from the moon. This right here in the middle is going to be our moon, and it's going to block out the light from the sun. And we have this path of totality, this path of like where the complete shadow of the moon is going to be hitting the Earth. Now, outside of that, we have this penumbra region here. So while it's still a shadow, it's not a complete shadow, but we'll notice that parts of the sun are going to be blocked off from that way as well. So as you look at it, it won't be a complete total solar eclipse, but you'll still see the moon crossing in front of the sun that way. One of the interesting things is in August of 2017, we will have a total solar eclipse travel across the United States, and the path will take it from about Oregon to Georgia. So it'll be the first time that it'll actually come across in a long time that we'll have the opportunity to see it. So a solar eclipse is when the moon travels in between the sun and the Earth. Okay, so let's talk about a lunar eclipse. A lunar eclipse is when the moon is going to travel through the shadow cast by the Earth. So we can see that the sun is going to shine its rays down here on the Earth. And what we'll notice is there's going to be this shadow cast. And we have both, again, the umbra, the complete shadow, and the penumbra, which is kind of like a side shadow, not totally dark. And when the moon travels through this, that's when we get a lunar eclipse. On a total lunar eclipse, that's where the complete portion of the moon is going to travel through this umbra, and it results in this kind of reddish moon color. Sometimes they'll call it a blood moon, and it's just because of the reflective nature of the light coming off of the Earth's atmosphere. It's going to bend a little bit, so kind of like how sunsets are red sky, and that's why it'll kind of shine up in that little reddish color. So a solar eclipse is when we block out the sun. A lunar eclipse is when the moon travels through the shadows of the Earth. And those are our two types of eclipses. As always, good luck on your quiz, and we will see you in the next video. Aloha and welcome to our video on the Earth's moon. In this video, we'll describe how the physical features of the lunar surface were created. We'll also explain the history of the moon. Okay, so let's take a quick look at the moon. Remember that Aristotle felt that it was a perfect sphere and unblemished, but Galileo, with his telescope, was able to see that there were features on the moon. So let's look at a couple of these features as we go through. Some of the first ones that you'll notice is you'll see this word mar here, okay? And that's basically like a sea. So what it is the large flat area, and we have the Sea of Tranquility, or Mar Tranquillatis, and right over here is where we landed with Apollo. We also have Oceanus, which are going to be these larger, darker areas, and that's believed to have been like magma and lava that reached the surface and kind of smoothed it out as the moon was still forming. We also notice that there's a whole bunch of craters, and a lot of these craters are going to be named after astronomers. So we can see that we have Copernicus over here, and we have Kepler over here, and we can look for some other ones. We have Ptolemy over here. So they named a lot of these craters after scientists and astronomers and things of that nature. So when we look at the moon, there are features that we can look at, but how did these features come to be? Well, that's what we're going to discuss in the next slide here. Okay, so let's start off with the formation of a crater. The first thing that's going to happen is we're going to have this meteoroid impact that's going to come down and it's going to hit the surface of the moon. When that happens, it's going to create a little hole, but it's also going to send out this wave of compression where everything gets kind of squished together because we made this hole happen. That's going to, we see here, it's going to send out this energy, and then that energy is going to come back as a rebound. And when it does so, it's these two forces here that kind of form the walls of the crater. We also can see way down here that we have this ejecta material that's going to be thrown out. So the newer craters are going to have a little more pronounced ejecta, and we call those the rays on the craters. And we'll see that here in the next slide. Okay, so let's take a look at some of the topographic features of the moon. Now, on the moon, we talked about craters already. We can have large craters and small craters. Some of the older craters are going to be lava flooded because we had some volcanic activity while the moon was forming. These younger craters, the youthful ones, we talked about these rays of ejecta being seen. Now, we have highlands on the moon because when it was forming, there were parts that were kind of crushed upwards and we made some mountains. We also have some trenches, and we call those rills, and the rills were once thought to be canals. So that's why they thought there might be people on the moon or aliens on the moon, because we had these canals and that would be a way that they could travel. We also talked briefly about these Mars, and the Mars are going to be like your seas, a flat region, so kind of like a plane. It's just going to be a big, broad, flat area there. And then also we talk a little bit about lunar regolith, which is going to be kind of like the smaller rocks, the dust, the clays, and things like that that we can see on the moon as well. So how did the moon form? Well, we believe early in Earth's history, Earth was impacted by something, be it a meteor, be it an asteroid, something large that impacted the Earth. And when it did so, we can see the impact here. It created this dust ring, so to speak, around the planet. We could see that here. And that's kind of like how we formed, how the Earth formed in the solar system. So there was this area of dust, and as the particles collided and grew together, the gravity of those increased and they attracted other ones, and it basically cleared the field, and that's how we formed our moon here. So the moon formed much the same way the Earth did. However, the moon's a lot smaller, so it was able to cool completely. So unlike the Earth, which is still going through plate tectonics and things of that nature, we don't see that in the moon because the center of the moon, the core of the moon, is kind of cooled down to the point where we don't have plates and we don't have that convective currents going on that would cause the moon to shift. So our moon probably came from a collision, and it's just the remnants that were blown into space that coagulated together and formed the moon. Okay, as always, good luck on your quiz, and we'll see you in the next video.